We notice in this integral that there is a variable squared plus a constant squared. And we know that from our commutative property of addition that x squared plus 4 is equal to 4 plus x squared. Therefore, we can use our trigonometric substitution in order to solve for this integral. First things first, we transfer our constant outside the integral, and then we let x be 2 tan theta, since it is a constant plus a constant squared plus a variable squared rather, and our dx be 2 secant squared theta d theta, our a being equals 2, and our a squared equals 4. With our substitution, we also calculate for the value of our tan theta and our theta itself, which is our tan x over 2. Plugging in the values, we get 2 secant squared theta d theta all over the quantity 2 tan theta squared times the square root of the quantity 2 tan theta squared plus 4. Simplifying the squares, we get 4 tan squared theta for both. And as you can see here at the radical, we have the common term 4. Therefore, we can factor out 4 as such. This becomes 4 tan squared theta plus 1. And then the square root of 4, we can move it out and turn it into 2. Now, using our trigonometric identities, specifically the Pythagorean identities, we know that tan squared theta plus 1 is equal to secant squared. Therefore, we can plug in secant squared inside the radical as such. And now, we also multiplied our coefficients, 2 and 4, to form 8. Now, as we can see here, there's a squared secant inside of a radical, so these two cancel out, the radical and the square. And also we can see that 8 is divisible by 2, so 2 cancels out and 8 becomes 4 as such. Moving on, we can see that what's left of the denominator, we have a secant, and here we can cancel out this secant as there is a secant squared at the numerator. So we cancel the square, cancel out the secant, and we get such value. And also there is a constant of 1/4 inside of our integral. So we move it outside. That's why we get a 5/4. And this is what our integrand looks like at the moment. Using our trigonometric identities, we know that secant is equal to 1 over cosine. In this case, secant theta is equal to 1 over cosine theta, and tan squared theta is equal to sine squared theta over cos squared theta. And now, using our laws of fractions, we multiply the numerator by our denominator, which gives us these values. And since there is a cosine at the bottom and a cosine squared at the top, we cancel out the cosine at the bottom and the square at the top, which leaves us with these values right here. And now, we can use substitution in order to solve for the integral, or the antiderivative. So let u equals sine theta, du equals cosine theta d theta, which gives us the following: du over u squared. And so we turn u squared into u raised to the power of -2, so we can make use or utilize the power rule as such. So now we have 5/4 times -1 times u raised to the power of -1. Since we use the power rule, so every exponent, or every instance of the exponent, it gets added with 1, plus c. Now, simplifying it, we get -5 over 4u plus c, and substituting the value of our u, which is sine theta, we get -5 over 4 sine theta plus c, and substituting the value of our theta, as we previously found out that it was arctan x over 2. So we get this, and by using our trigonometric identities again, we get the following value for our sine arctan x over 2, which is this one. And then it's basically simply simplifying the equation. So this is a fraction, a whole number divided by a fraction. So we find the reciprocal of the fraction and multiply it by the original fraction. So 2 and 4 can be divisible. 2 can be cancelled out. 4 becomes 2. And as such, it's simply a matter of simplifying everything.